Hi everyone, and welcome to the boost converter video for 3107 Power Electronics for Group 3 in 2024. Now, let me magically snap my fingers and disappear. Right, so the typical boost converter circuit will look like this, with an inductor in parallel with the switch and diode, and in parallel with a capacitor and the load. So the aim is to switch on and off to produce a duty cycle, which we'll cover later on. So for the first mode, when the switch is on, right, it will boot the inductor and the capacitor in charging mode. And the second mode, when the diode is on and the switch is off, this will cause the inductor and the capacitor to discharge. So the on and off is the switching device, which we will use a MOSFET and N MOSFET, and the N MOSFET gate will be connected to a pulse, which will be produced by the 555 IC in the astable mode. So for the VCC itself, we will connect to an R1 and R2 here, which will actually help to produce the pulse. So what we need is a T on, which the formula will be here, right, which will produce the on time, and the off time will be below that. So we get 69 kilohertz of frequency, which is nice. So again, there's two modes, A and B here. The A when the MOSFET is on, and the B when the MOSFET is off. The duty cycle is very important as it matches the duty cycle needed to step up from 12 to 24 volts, as I'm going to write here on both modes. So next up, we need to calculate the inductor value and the capacitor value, which we use the formula here, which is VL equals to L over di dt1, which will lead that the inductor must be above 4.3694 millihenries. And next, for the capacitor, we will need to find out the capacitor value, which is IC over equals to C dV dc or dt1, which calculated the C must be more than 3.790 microfarad. Next, we'll be moving on to the output side. A voltage divider will connect it to the inverting input of the OpAmp, while the non-inverting input will connect it to a V-reference. The output will be connected to the pin 5 of the 555 IC. Now, if the inverting input is higher, it will cause the output to be inverted down, and then this will actually decrease the duty cycle and lower the output voltage itself. In another case, if the non-inverting input is higher, the output will go high and will actually increase the duty cycle, which will in turn increase the output voltage. Now for an OpAmp as a comparator, the aim is to make sure that the V plus is equal to the V minus, which will eventually stabilize the duty cycle, which in turn will stabilize the output voltage. And this is our final PCB design for the boost converter. The first is the capacitor, the diode, the 555 IC, the LM358, which is the OpAmp in comparator that we mentioned previously. Next is the capacitor that is in charge of the 555 IC, the RRF540N MOSFET, the trimmer, and the inductor. And below here is all the SMD Resistors that are in charge of the voltage dividers. The first output is 8 LEDs in series, which in turn will produce about 23.9 to 24.0 volts. It may look stable, but in a close inspection, there is a ripple, which Vmax is 24.39 volts and minimum of 23.65. As for the second pulse, here is the V pulse that I mentioned. At peak is 11.94, which is connected to the VCC, and this pulse is actually the VC VCAP that was connected to the 555 IC. Next is the comparator. As seen here, when compared both waveforms, they are at the same, which matches the comparator mode. And this is the testing of the red LED tower and the blue LED tower that almost blinded our group member.